So at this point, we're getting into part 3 of the text, which is actual database design. So we're getting away from the part where we were doing the kind of modeling, data modeling of our database system. So let's look back real quick. If you don't have your text with you, go ahead and grab your text, and I'll wait. So look at figure 1-7 on page 19, and we've already completed the planning and analysis steps of our of this process. So the analysis portion was to create that conceptual data model. And that's what we've been doing up to this point. And I've mentioned a few times that the models that we've created to this point, you should not necessarily picture each of those entities translating directly into a table in our database, and we'll see that when we get into chapter 4. So we are looking into part 3, which gets into database design, the logical database design and the physical database design. Now chapter 4 will convert our conceptual data model into a logical database design, and which will include the normalization of that database. Now make sure that you look at the appendices in this text, because there's some really good information back there. Appendix B kind of adds on to the normalization information that's provided in chapter 4. So take a look back at that. Chapter 5 is going to get into our physical database design and its performance. So early in the intro in chapter 4, it mentions that there are a lot of data modelers that kind of develop their conceptual model as well as the logical design all at one time, and now, and that's fine for those seasoned modelers that are able to do that. For our purposes, we're going to do we've already completed the conceptual design, and we're going to translate that into our logical model. Of course, every chapter has a list of objectives. Review those objectives, because those are what we're going to be focusing on in these video notes. And again, there's tons and tons more information in addition to what's focused on with these objectives, but let's concentrate on that for the purpose of this class. Okay, so we are finally getting into an area where we can start talking about tables. Now, tables in chapter 4 and from with 5 and 6 as well, tables and relations are going to be synonymous, and of course tables contain rows and columns. We're also going to be talking, and that covers the data structure itself, and then we're also going to be talking about the manipulation of that data and some SQL operations that can be used to modify it, and the data integrity, which is pretty critical, and we'll get into that when we start talking about normalization and the like. So the data integrity just means that we have consistent data regardless of what a user might do to it, or what data objects might be coming into that database, and we'll see that here in a sec. So a relation or a table is a two-dimensional table of data. It's basically, it can be considered a flat file. There are a lot of people that equate that to a spreadsheet of sorts, where you have a list of rows and columns, and then these are the requirements for that table or a relation. So now that you can read through these in your text, but one very important note is that a relation must be in first normal form, and we'll get into first normal form here in just a sec. But that's if it's not in first normal form, it cannot be considered a relation. The relations correspond to with the entity types that we've been using in our past data models, with many-to-many relationship types. the rows correspond to the entity instances with many-to-many relationship instances, and the columns, of course, correspond with attributes. Now, keep in mind, and this can be confusing to some, the word relation in a relational database is not the same as a relationship. A relation is now a table that can contain data. The relationship is that relationship between one entity and another entity in an ER model. So two of the primary fields that we're going to be interested in for this chapter anyway are going to be the primary keys and the foreign keys. Now the primary keys were they equate to our identifiers back in our entities that identified each entity type. Now the primary key is going to be very important because those keys have to be absolutely unique to every record in that table or in that relation. There can be no possibility that they could be the same. For instance, you could use a social security number. Of course, that's not used anymore for this type of purpose for security reasons. The foreign keys are the keys in the related entity that ties back to the original entity or the original relation, and we'll see that here in just a little bit. Keys can be simple, containing a single field, or a composite, which will be many or multiple attributes. And figure 4-3 shows an example of this. The customer ID is the primary key for the customer relation, and then customer ID is the foreign key in the order relation. And now notice that order line has a composite primary key of order ID and product ID. So real quick, I wanted to touch on this. The domain of an attribute is the list of values that can be entered in that attribute. For instance, if you take a look at table 4-1 and look at the attribute of order date, of course that domain is a date. So a value of April 20th of 1968 would be something within that domain, but New Orleans, Louisiana would not be in that domain. And one more thing, I've mentioned this in a couple of videos in the past, that the primary key must contain a value and may not be null. Now there's a description of null in this chapter somewhere that kind of contradicts what the computer science definition of null is. Null is the absence of data. That doesn't mean that it's zero or some other value, some arbitrary value that happens to be in that memory location. Null means there's no data. So it's very important that primary key be some value that is unique to identify each record individually. The text talks about on page 160 referential integrity, and they use a rather complex method. So the text states, the rule states that any foreign key value on the relation of the many side must match the primary key value on the relation of the one side, or the foreign key can be null. So basically what that means is that the foreign key in one relation must tie back to a primary key in the associated relation. Now if that relationship is optional, then that foreign key can be null. If that relation, or the cardinality more precisely, is mandatory, then that foreign key must contain a value. So this figure 4-5 kind of demonstrates that. Customer ID is the primary key of customer order ID, is the primary key for order. And now notice that customer ID is used as a foreign key in the order relation, but notice that it has a dashed line under it. That means that that is optional. In other words, customer can place an order, but it does not necessarily have to place an order. It actually can place many orders. So that is optional, so that line is going to be dashed. Now, again, pay very close attention to this, because these are the formats and the syntaxes that we're going to be using when we submit assignments and discussion posts. So, and also on order line, notice that there are two attributes here that are underlined as primary keys, because this is a composite primary key. One has a reference to the order ID, primary ID, and then or the primary key, and then product ID refers to the primary key for product. So this is the code that I sent you guys a couple of days ago, or the text version of that. And notice the referential integrity constraints between the order table, or ordered underscore T table, and the customer underscore T table. And notice that that the foreign key is the customer ID, which references the customer T table and the customer ID primary key. So study that very closely. That's there's also some similar referential integrity down in the create table. I'm sorry, the order line T table. So take a look at that and let me know if you have any questions. So we're at a point now that we are converting our regular entities into relations. So notice on page 164, figure 4-8, they're converting the customer entity into a customer relation. And notice that it's basically one for one in terms of the attributes coming down from the entity into the relation. But now notice what happens with our composite attributes. It effectively just turns into multiple attributes that that are added into our customer relation. In other words, it's no longer a composite. Notice what happens here when we are mapping an entity with multi-valued attributes, and I believe we touched on this in chapter 2 or 3. Where we effectively have to create an associative entity, or basically create a new table or a new relation that's going to contain that multi-valued attribute. So in this case, we have a multi-valued attribute which was skill, that was all part of the one entity. Now notice that we now have two relations, one called employee that has an employee ID as the primary key and a couple of attributes. And then there's another relation called employee skill that has two primary or a composite primary key of employee ID tied back to the employee relation, and skill, which is the skill that that employee earned. This is kind of similar when we are mapping weak entities into relations. So let's take a look at this. We have an employee with their dependents, and notice that the dependent has a dependent name that is a composite of first name, middle name, last name, and date of birth. I'm sorry, first name, middle name, and last name is the composite, and that turns into the dependent with the primary key is a composite of first name, middle initial, last name, and the employee ID of the employee that they're a dependent of. These are some pretty important steps in mapping our binary relationships. Notice that a one-to-many relationship the primary key on the one side becomes the foreign key on the many side. So now remember that, because that's going to be very important when we start doing our conversion from the data models that we had in the previous chapters to the relations that we have now. And of course, a many-to-many relationship, you can't really do that in SQL. So you have to create a new relation that's basically from the cognitive model is going to be an associative entity that will turn into a new relation with primary keys of the two entities as its primary key. So this is an example of mapping a one-to-many relationship. So one customer can have many orders, or since it's optional, may not have any. So notice that the customer ID, of course, is the primary key in the customer relation, and customer ID is the foreign key in the order relation. But again, notice it's underlined, so it is optional. And here we're talking about the mapping of the many-to-many relationship, and we've seen this already, where we have to introduce a new relation or a new entity into this figure. So we have employee and course, and of course many employees can take many courses, and many courses can contain many employees at one time. So let's see how that happens. So we effectively create a new entity called certificate that has a composite primary key of the employee ID and the course ID, and it has another attribute called date completed. And these, of course, are our original entities of employee and course. And of course, the one-to-one relationship that is pretty easy. You have a nurse that is the head of a care center. Now, not every nurse is the head of a care center, so that can be optional. But every care center must have a nurse or a lead nurse. So that is mandatory and one, and this is optional one. From nurse to care center is optional one, and then care center to nurse is mandatory one. So this is pretty easy how that's set up. So nurse ID is the primary key for the nurse relation, and that is used as the foreign key or the nurse in charge in the care center relation. When we talk about the mapping of the associative entities, we have identifiers that are not assigned and identifier assigned. And the identifier not assigned will result in the default primary key for the association relation composed of the primary keys of the two related entities in the many-to-many relationship. And then the identifier assigned is effectively having its own primary key. So this is an example of mapping an associative entity. We have two entities, one called order and one called product, and then the associative entity is called order line with the attribute ordered quantity. And notice that this associative entity turned into its own relation called order line that has a composite primary key of order line and product ID, which are the primary keys of the two related relations, and then it has another attribute called or that contains ordered quantity. Now this is compared to an associative entity with an identifier. In this case, we have customer and vendor with our two entities, and then the associative entity is shipment with a shipment ID as the identifier. So, and we take a look at that now. Notice that it still has the primary keys from our two two relations associated in that new relation called shipment. Now, shipment still has a primary ID as a primary key, but and that is the primary key for that relation. Now, it still has customer ID and vendor ID, but those are effectively just attributes at this time, and they're not part of that primary key. In other words, they're not a part of a composite primary key. So this was something I wanted to touch on real quick. The book doesn't get into great detail about this because SQL really doesn't do supertypes and subtypes very well. But anyway, so these are the details of that supertype to subtype relationship. Of course, this is how the that entity relationship would look, and this is how the resulting logical model would look. So we have an employee and the hourly employee, the consultant, and the salaried employee, and all of these have tie back to the employee relation with the employee number. Now, of course, these are they have different attribute names when they land in those subtypes. Now, as this figure demonstrates, these are implemented as one-to-one relationships between the supertype and the subtypes. So, data normalization is a critically important part of our database design. Now, I can't get into the detail the book gets into, otherwise, again, you would be with me for a couple of hours. But I wanted to cover from about 30,000 feet the normalization, the first normal form, second normal form, and third normal form, and at least get a general understanding of that. Now, the text indicates that normalization is a formal process for deciding which attributes should be grouped together in a relation so that all anomalies are removed. And we'll talk about anomalies here in just a moment, but it further indicates that normalization is the process of decomposing relations with anomalies to produce smaller, well-structured relations. And having those well-structured relations is going to be very, very important. Now, hopefully this class will at least give you a good idea of what that good structure should be, but of course that type of talent comes with practice and actually doing it. The text indicates that a well-structured relation is a relation that contains a minimal data redundancy and allows users to insert, delete, and update rows without causing data inconsistencies. And we'll talk about that here just briefly. But an insertion anomaly means that when data is added into a table, it creates duplicate data in that table. A deletion anomaly may be when data is removed from that table that it affects the data in other tables, and we'll kind of talk about that here momentarily. And then, of course, the modification. If you change something in a table, it can create problems within that table or within a relationship to another table. And now this slide indicates that a general rule of thumb is a table should not pertain to more than one entity type, and that gets into we talked briefly about the ternary relationships when we were doing our entity relationship models, and we just don't. That is almost never ever seen, but when it is, you of course have to create an associative entity that generates a new relation or more, and get rid of that. So just stay away from that. This is figure 4.22. I'm not sure what page this is on, but so it talks about the first normal form, second normal form, and third normal form. And of course, page 156 indicates that a table that contains one or more multivalued attributes is not a relation. Therefore, the first normal form is to remove those multivalued attributes. And we'll see how to do that momentarily. And then the second normal form is to remove partial dependencies. We'll get into that. And then the transitive dependencies, we'll also see how those work. So one very important step in this process is to determine the functional dependency. And basically what that means is that the value of one attribute determines the value of one or more attributes. And we'll see how that works here shortly. And we've already covered what a candidate key is. It's basically a unique identifier or an attribute that can qualify as a unique identifier. And one important detail is that each non-key field is functionally dependent on every candidate key, and we'll see how that works here in just a sec. So first normal form, first of all, means no multi-valued attributes, and we've talked about that and what we need to do to get rid of that. Every attribute value is atomic, which means that it contains one value. Take a look at figure 425 on page 180, and notice that this is not in first normal form because it has a number of rows that do not contain the primary key and order date and some other values that should be in those rows. Now take a look at figure 4-26 on page 181, and this is in first normal form because all the relations do. All the records do have some value in those locations. Now this is figure 4-25. And notice that that this is not a relation because there are some values that do not contain data. But now this is figure 4-26, and now notice that it indicates that this is a relation, but not a very well structured one because you have duplicate information in some of these values, and we'll learn how to get rid of those. Now, due to these duplications of values in what is a candidate key, our order ID, we've had to make a composite primary key to include the order ID and the product ID to make each value or each record unique. Now, these are just some of the anomalies that can be experienced with that table in 4-26. If a new product is ordered for order 107 of existing customer data must be re-entered, causing duplication. And we certainly want to reduce as much duplication as possible. If we delete the dining table from order 1006, we lose information concerning its items finish and price. So let's take a look at that. Delete table from order 1006. Dining table from 1006. We lose some information on the product finish, which was natural ash, and that's the only record containing that value. And then if we change the price of product ID 4, requires update of multiple records. So let's take a look at that. So if we look at ID 4, we'll have to change this record and this record to make sure that everything is consistent. And again, those are some of the anomalies that that can be experienced with this table. Though it's in first normal form, we still have some data anomalies that we have to contend with. So once we achieve first normal form, the next step obviously is second normal form. And second normal form is first normal form. In addition to every non-key attribute is fully functionally dependent on the entire primary key, and we'll see how that works in one of the figures here in just a moment. Additionally, every non-key attribute must be defined by the entire key, not by part of the key, and then no partial functional dependencies, and we'll see that in just a moment. So, by the way, a partial functional dependency is when a non-key attribute is functionally dependent on part, but not all of the primary key. And we'll see how that works here in just a sec in Figure 427. So, order ID is functionally dependent on order date. I'm sorry, has partial dependency on order date, customer ID, customer name, and customer address. And then customer ID is dependent upon customer name and customer address, and product ID has a partial dependency on product description, product finish, and product standard price. And then order ID and product ID are have full dependency on order quantity. So this is not in second normal form. So we have to get rid of these partial dependencies and the transitive dependency. So we've kind of broken that down into a few relations, and we have one relation called order line that is in third normal form, and that contains order ID and product ID as the primary ID, and order quantity. And then we have product, which is in third normal form, which has product ID as the primary key, and then product description, product finish, and product standard price. And then order ID that has a transitive dependency. So this is still in second normal form. So let's take a look at that and compare this single relation to this figure that has three relations. Now, we haven't gotten too deeply into third normal form yet, but these two relations are indeed in third normal form, and this is in second normal form because we have gotten rid of the partial dependencies that once existed in the initial relation. And of course, to achieve third normal form is going to be second normal form plus no transitive dependencies, or functional dependencies on non-primary key attributes. And we'll see. Okay, please forgive me. I started to run out of disk space there, so I had to clean some stuff up, so I don't remember where I was. So anyway, getting back into third normal form, that is the second normal form plus no transitive dependencies, which, if you notice on this figure, we had these two relations in third normal form because there were no transitive dependencies, but we still had a transitive dependency on the customer order. So it is indeed in second normal form, but not third. So let's take a look at how to get rid of that. Now there's a note on here that says this is called transitive because the primary key is a determinant for another attribute, which in turn is a determinant for a third. So the solution to that is a non-key determinant with transitive dependencies go into a new table. So non-key determinants become a primary key in the new table and stays as a foreign key in the old table. So let's take a look at that. So let's roll back a couple of pages here, and we'll see that customer order was again in second normal form but not third. So we'll split that into two new relations, one called order and one called customer. And both of these are in third normal form because we've gotten rid of the transitive dependencies. The text talks about enterprise keys, which are primary keys that are not just unique to the table, but are unique to the whole database. So in other words, there is not those primary key values are not duplicated anywhere in the database. And that kind of moves into an object-oriented type system. And if you've taken C++ or Java, you know what that means. But it's a really good idea. Having done enterprise administration for quite a while, it's pretty important that we have those unique values that are unique to the world. So that's really all I wanted to cover on this chapter. Again, there's like every chapter, there's lots and lots of information to be covered. I kept this under 40 minutes. Please read this chapter in detail and make sure that you have a good understanding of the information contained therein. If not, let me know and we'll cover it. Post those questions in the discussion areas, or come join me during the chat session on Saturday. I think I'll be able to do that chat session this Saturday. So get those questions together and we'll talk about it.